Now let's use Colab to better illustrate how this algorithm works. So first, we will just wrap up all the TSP algorithm in previous class to be the building blocks we will use in solving VRP. And then similarly, we will first initialize our VRP problem. In illustration, we will have 20 customers and then with one depot, so there will be 21 nodes. And then we generate the location from 0 to 10, which is uniform distributed. And then the demand here, we just generate with uniform integers from 1 to 3. And then we assume the capacity of each truck is 8, and then the number of truck needed. Similarly, we can calculate it based on the ceiling function of the summation of demand over capacity. So here is the illustration of this current example. The blue dots with the size indicates the customer demand. So the smallest points indicates the demand is 1. The big dots indicates the demand is 3. And then there are some intermediate dots like this will be 2. And then the depot is on the left-hand side, which is indicated by the red square. And now let's see how we realize our algorithm. The first step, we will try to randomly generate M centers for all the customers. To realize this, we just randomly permute all customers from 1 to n, and then we select the first m customers as the center. So this is a purely random generated customer centers. And then we call this generated center as seed customers. And then all the other customers are excluded. So the other customer can be just calculated. We divide the entire group of nodes by depot 0, and then seed customers, and then all other customers. So we divide our nodes into 3 groups. So here we have 5 trucks, and then our seeds or the selected customer centers are customer 6, 11, 12, 14, and 18. And then all the other customers are in the following 1, 2, 3, 4, 5, 7, 8, 9, 10, blah, blah, until 20. Then our task is trying to allocate those other customers to each center in the seed customer. Now we will introduce closeness. From this calculation, we can calculate the allocating cost, which is DIM, based on the calculation of the distance from depot to customer, customer to center, center back to depot. And then there's another direction from the depot to the center, and then from center to customer, and customer back to depot. We take the minimum value of these two, and then minus the travel distance from the depot to the center. Here, to better utilize our minimum cost flow assignment problem, we guarantee that allocating cost or the closeness is integers. So we multiply 1000 on this value and then round it to an integer to differentiate the distance from the customer to the centers. For example, after this allocation, the customer 1 is in the other customer set, 6 is in the seed customer set. You can see the closeness from the customer 1 to customer 6 here is around 575, which is just a measure. So the smaller value indicates a smaller distance. The larger value indicates a larger distance. And then we will introduce a package called NetworkX, which is a very famous package in Python, introduce the graph structure and provide some fundamental algorithm widely applied in graph structure. So which we will use this to calculate our minimum cost of flow assignment problem. So the first step we initialize is a directed graph. Actually, on the one side, this is our centers, which is our seed customer. And the other side, which are our other customers. So we will create the structure, graph structure, where each of this edge indicates a certain cost, calculated by the allocating cost, which is our DIM. Flow demand on each seed is the capacity minus the demand at the seed. And then the demand as the customer is their demand, which need to be covered. So we generate the seed customers and the capacity is to be consumed. And then for the other customers, the demand is what their demand is. And then for each of these edge, we connect the seed customer to the potential other customers given that the weight is their closeness measure. And then remember that if the capacity of the truck is not fully utilized, we provide a dummy node as our dpot such that the total flow to be assigned are 0. And then we will introduce this minimal cost flow assignment problem, and then we can get our optimum solution from the flow dictionaries. Here, after we solve this problem, we can print it out. You can see this is a pretty fast algorithm, and then the center node 6 will be grouped together with customers 3, 10, 15, 17, 19, and then together with their demand. And then this is center 11, this is center 12, center 14, center 18. So interestingly, you can observe that the customer 16 is assigned to both center 14 and center 18. This is feasible because customer demand can be decomposed into small volumes, such as the total capacity within each group is not beyond the truck capacity. This may not be the optimum solution. And then after we organize the results, we can form subgroups, and then in each subgroup, we add the dpot, the center. This is a dpot, this is a center, and then the rest are the other customers. Okay, after we have all these groups, 1, 2, 3, 4, 5, we have 5 groups, and we have 5 trucks, so we will solve 5 TSP within each group. Here we use the TSP building block just to guarantee that our subgroup is correctly interpreted to the parameter of our TSP problem. So here our parameter, the sequence, the cost, the number of the total customers within this subgroup, max number of iteration for the calculation of the TSP method is introduced here. So for rapid solution, we just use the 2-opt heuristic algorithm. So definitely you can apply more advanced TSP algorithm, but for our demonstration convenience, we will not cover them. You can definitely solve TSP with MIP solver or with simulate annealing algorithm and so on. But here we just use the 2-optimum heuristic algorithm, which is pretty fast. And then here in solving the TSP with the solution of TSP, we can get the VRP solution. This is a dpot, and then the customer signed guarantee that the capacity of each truck is satisfied.